Hi everyone, my name is Mantalena Sarafianou and I'm a scientist at the Institute of Microelectronics in Singapore. This presentation is about the feasibility study on relative humidity sensing using silicon on nothing pMUTs. To date, ultrasonic sensors have been used for environmental parameter sensing in air and other media for the monitoring of parameters like temperature, humidity, wind velocity, and liquid density. Specifically for temperature and humidity, environmental monitoring would be critical in settings such as air conditioning management and preservation and conservation of artwork in museums and art galleries. The current state-of-the-art in humidity sensing includes wet-dry and hair hygrometers, dew-point instruments, and polymer-based capacity sensors. These sensors can provide accurate estimates of the humidity, however, they have certain drawbacks. First, they can monitor humidity localized to the point of interest, which means that if we want to monitor spatial average humidity values, we need to deploy a large number of these sensors in the field, which would impact the cost. Second, the sensors must remain within moist air, and therefore the addition of dirt on them may lead to measurement errors. And finally, they may exhibit undesired hysteresis due to the response time during moisture absorption and dehydration. Although pMUT arrays specifically designed for humidity monitoring have been proposed in the literature, there is a requirement for general-purpose pMUTs with suitable signal processing methodologies for sensing humidity. Such a solution could have a dual advantage. First, it can reduce the cost of the simulation, design, fabrication, and optimization of these application-specific devices. Second, it can enable the use of standard pMUT arrays for humidity sensing in parallel with other applications like ranging or imaging. The work presented here today investigates for the first time the use of silicon on nothing pMUT arrays for humidity sensing. Initially, we looked at the theoretical relationship between the attenuation coefficient and the relative humidity, which is defined by the equation you see on the right-hand side of the slide, considering a specific frequency of operation. In the case of this work, we considered pMUTs with a resonance frequency of 1.15 MHz, and therefore the theoretical curve between the attenuation coefficient and the relative humidity can be seen in the figure on the right-hand side of the slide. By looking at the curve, we can see that the attenuation coefficient tends to increase proportionally with the relative humidity, and also that the attenuation variation along the vertical axis of this figure is less than 10% for the full range of relative humidity levels. All in all, there is a close to linear relationship between the attenuation coefficient and relative humidity, when the relative humidity is greater than 30 to 40%. The signal processing methodology that we could consider in this work consisted of the use of the Pearson's correlation coefficient to map a relative humidity value to a received signal, considering a number of processing steps. First, a pulse echo baseline measurement is captured at every designated relative humidity, and all these measurements refer to the reference dataset. Second, another set of pulse echo measurements is collected with the relative humidity decreasing this time with the same step as before, and all of these measurements define the measured dataset. In the third processing step, each signal from the measured dataset is compared against every signal from the reference dataset by computing the correlation coefficient, which is given by the formula that's provided on the middle of the slide. The numerator would correspond to the covariance matrix between the two signals, whereas the denominator would refer to the product of the deviations of the two signals. A value of the correlation coefficient close to 1 will denote a good similarity between the two signals, mapping effectively the measured signal to the specific relative humidity indication of the reference signal. At the bottom of the slide, you can see the experimental setup that we considered for the validation of the signal processing methodology. We considered two pMUTs that were placed at a fixed distance from each other. And then this pMUT setup was placed inside the temperature chamber. One pMUT acted as a transmitter and was connected to a function generator, whereas an oscilloscope was connected to the other pMUT in order to record the received data. The chamber's temperature and air pressure were kept at fixed known values, whereas the relative humidity was varied in the range of 35 to 95% in 10% increments. We also considered an external thermometer and humidity sensor in the test setup to provide reference baseline readings. Both reference sensors were controlled by an Arduino kit. Initially, we computed empirically the relationship between the attenuation coefficient and the relative humidity from the measured data, which was expressed by the equation you see in this slide. The resulting curve can be seen in the figure on the right-hand side of the slide. Qualitatively, the experimentally computed attenuation coefficient increases linearly and proportionally with the relative humidity. This is similar to the theoretical observations we made earlier on in slide 5. However, a direct quantitative comparison between the theoretical and measured observations is not possible because of the value mismatch. Moving now to the validation of the signal processing methodology. Let's take, for example, the measured signal at 35% of relative humidity, which is denoted by the blue curve you see in the figure on the right-hand side of the slide. We can see that for the blue curve, the correlation coefficient is closest to 1 for the reference signal at 35%, showing that the method can correctly map the measured signal to a given relative humidity, in this case the relative humidity of 35%. Similarly, if we look at the measured signal of relative humidity of 45%, which is the red curve, we can see that the correlation coefficient is close to 1 for the reference signal at 45% over here, showing again that the method can map the measured signal to the 45% relative humidity. And the same case can be made for the rest of the measured signals. In contrast, the reference humidity sensor that we considered in the experimental setup results in an average accuracy error of approximately 2.4%. To conclude, the signal processing methodology for accurately mapping a measured signal to relative humidity indication was proposed using a pair of pMUT chips. The proposed method leads to a binary answer with 100% accuracy in mapping to the correct relative humidity level for fixed temperature and pressure environments. The sensing setup successfully maps the received signals, capture an unknown relative humidity actual condition to the correct relative humidity indication based solely on the linear variations between the actual and the reference signals. The next step of this work will include to develop a combined approach for temperature and relative humidity sensing for settings where both these parameters change over time. I'd like to thank you very much for attending my presentation. Unfortunately, this is a recorded presentation and there will not be any live Q&As. However, one of my colleagues and author for this work, Dr. Choong, will be among the audience, so feel free to approach him to ask for any questions you might have with regards to this presentation. Alternatively, feel free to contact me. I can be reached on the email you can see in this slide. Again, I'd like to thank you for attending this presentation. Enjoy the remaining of the IEEE Sensors Conference. Goodbye.